Hi. I was expecting 2 students and maybe 1 student listening. So I think I can start. Can you hear me?
I hear you, Professor, but I can't see you.
You cannot see me?
No.
Oh, so maybe I should ask to the people in the office. Apparently the student cannot see me. Ah, okay. Now, can you see now?
Yes, now I can.
Tell me also if I'm writing too small, or feel free to stop me at any time.
Okay, okay.
Okay. Hi. So I think we can start. So this year the course will be on elliptic partial differential equations. So elliptic PDEs. More specifically, actually, on the Laplace equation. More precisely, most will be on Laplace equation. Laplace equation. So let me explain to you what is Laplace equation, what are the problems that we usually have to solve when looking at a new PDE. So the problem is the following. So given an open set, given n larger or equal than 1, but n equal 1 will be not of interest essentially for us, so I put it, but we will study essentially n larger or equal than 2. So given n larger or equal than 1, open set, given some function f given also some function g defined on the boundary of omega, we are interested in studying the following Dirichlet type. So find, solve. But now solve, we have to be, we will see what does it mean during the course. Solve the following problem. So u is C2 omega intersection C0 omega bar minus Laplace of u equal f in omega, and u equal g on the omega. So what is this problem? What is this problem? First of all, this is a problem that there are various different ways to even to set the problem. So this way I write it here is in a classical form. So classical because this is the unknown, u is the unknown. We are looking for a function u which is C2 inside omega, in omega, that is continuous up to the boundary of omega, so on the closure. Why I need these 2 conditions? Well, because the problem is written in a classical form, which means that I want that this is valid at any point x in omega. So this means minus Laplace of u x equal f of x for any x in omega, where this symbol is by definition is the divergence of the gradient of u at x. Okay? The divergence of the gradient of u. So the minus here is, I prefer to put a minus. Some authors do not put a minus, but let's keep this convention to put a minus here. So this second, this object here is the PDE we are interested in. So this is classically written, which means at any point of the domain, this must be valid. Okay, this is the meaning in which I'm writing this PDE. And also, so and you see, I need U to be twice differentiable, because here I need U. I take the gradient of U, and then I take the trace of the Hessian of U at any point x. So it is clear that in order this to be well defined, it's preferable to have U C2, such a way that the second derivative are continuous, and therefore this is pointwise defined everywhere. Finally, this is so-called the boundary condition. So G is given on the boundary, and in order that so given G, say continuous, say, and given F continuous, if you want, given G continuous, this means again at any point I want U to be equal to X at any point. So this is, what is this problem? This is the PDE, second order PDE, two derivatives of U. This is the class in which we are looking for a solution. We will not work only in this class. This is just an example to write some problem. This is called the Poisson equation, usually. So this is called the Poisson equation. And has a physical meaning that I don't want to discuss, but it has a physical meaning because this is a PDE in divergence form. So it's very fundamental that this is the divergence of something. And you can find application in physics, in electromagnetism, and several other places. Okay, I skip all the physics here behind. So this is called the Poisson equation, and this is called the boundary, the Dirichlet boundary condition. Dirichlet boundary condition. Okay, so this is one way, one problem we are interested in. So the Poisson equation with Dirichlet boundary condition. There are several other ways and boundary conditions in the literature. Let us fix attention on this particular condition here. Concerning the references, I can quote some books. One book is by Evans, Partial Differential Equations. Then there is a book by this is general, not only, it is interested in several things, not only in elliptic partial differential equations, several other things. But a part of this book concerns this problem. Instead, Hilberger-Trudinger now is on elliptic. Now the title, don't remember precisely, but maybe second order elliptic. And then there are several other books and references. Maybe from time to time I will quote. Which is the problem? Which are the problems that we have to solve when we have a new problem like this? Of course, the problem are several problems. All are maybe related to one each other. Maybe one not really separate So one problem is, of course, the existence of a solution. This is, of course, one problem. Another problem is, of course, the uniqueness. And then the regularity. We will see something. And this, I mean, all of this depend on essentially, this problem here depend on the data that we have. The data of the problem, our data of the problem are omega, f, and g. From this data, we are looking for u, unknown u. Okay? And we will see that we will need some conditions on the data in order to have a solution from this problem, in order to speak about existence, uniqueness, regularity. Okay, this is a difficult problem. Let's start with simplifying it. So we put f equals 0. Okay, start to simplify. Start with simplifying. So the f here is assumed from now on for some time, is assumed to be identically 0. So this PDE becomes minus Laplace of u equals 0. Minus Laplace of u equals 0. Okay? Of course, the problem is non-trivial because there is g. So we are looking for a function which has minus Laplace equals 0 inside, but it is forced to keep the value g on the boundary of omega. Of course, if g is 0, u is 0, but there is nothing interesting. But the presence of g here makes the problem non-trivial even for f equals 0. Okay. Other questions? Questions is okay. Now, when f is equal to 0, this new PDE is called the Laplace equation. So we will need some time, some lectures to study this PDE. Okay? So the question is now, f is not there. An interesting question beside existence and uniqueness is the smoothness of u. Because here there is no right-hand side. So the second derivative, this trace here of the Hessian, it must be equal to 0, not equal to f. And if f is not smooth, of course, and we want this equal to f, Laplace of u cannot be very smooth. But if f is equal to 0, maybe we can hope that u is much more smooth than just to be C2 inside. So this becomes an interesting problem for Laplace, say. Another interesting remark is that, so this is a classical way to pose the problem. Then there is, so we have to keep in mind this because we want to compare this way of writing, at least posing the problem. So this way here, we want to compare with, this is a classical approach, so classical. With the semi-classical approach. They are not equivalent. Semi-classical approach, which is interesting because it gives immediately a connection between this PDE and the minimization problem in the calculus of variations. So consider, let me explain what do I mean with this. Consider omega now bounded, simplicity, bounded. G Lipschitz. Okay, Lipschitz. And consider the following problem. Define a set. Okay, sorry, from now on, so this f is equal to 0, eh? So there is no f here. I use now f I am used to do to another, okay, maybe I should not call it f, maybe f like this, f of psi equal psi squared over 2 for any psi in Rn. Consider, so this f is a slightly different symbol I want to distinguish. There is nothing to do with this f here. It's another f. Consider the following functional. Defined so you see, Lipschitz is convenient because Lipschitz means essentially the gradient of u is almost everywhere defined. Recall, this is a big theorem. It's a big theorem now, and I don't want to tell you just the statement, maybe Rademacher. So you are not supposed to know this, but it explains why it's nice to put the problem like this. So u in Lipschitz implies that u is differentiable in the classical sense almost everywhere. Omega. So grad u essentially is a function in infinity. So is a function almost everywhere defined, and this is in an infinity. So this means that this object is bounded, so this integral is well defined, essentially, on this class. Okay. Now, the problem, semi-classical approach, the semi-classical approach, which is different from this, but we can compare, do some comparison. So is we are interested in minimizing. Oh, this is called the Dirichlet energy or Dirichlet functional. So this f here is called the Dirichlet functional, or also Dirichlet energy. Okay. Functional. And the problem we are interested in is to minimize f of u such that u is a Lipschitz function and u equal to g on the boundary of y. So we are interested in, so this is another, probably you cannot see at the moment the relation between this approach and the other one, but these are strictly related. Okay, so I will try to explain to you why they are strictly related. This is interesting because it's a problem of minimization, and it involves just one derivative in writing it. There is no more than the gradient here. Okay, the Dirichlet, of course, you can see, is what? Is 1/2 integral of grad u squared x. Huh? So this is, let me rewrite it maybe more explicitly. If 1/2 grad u squared dx, u is in Lipschitz, u equal g on u. Okay. As I said, this is interesting because it involves just one derivative. In order to write it, in order to give a meaning to it, we have chosen the class Lip, which is, I hope I will have time maybe to say that maybe it's not the most natural way, because the most natural way would be to have this gradient in L2 and not in L infinity, but just to start smoothly, because putting this in L2 would need the Sobolev spaces. So I don't want now to discuss the problem of Sobolev spaces. So in order to avoid the machinery of Sobolev space, I start to work in this class, Lipschitz, no Sobolev. So which is the relation between why these problems are related? Again, let me stress once more. In order to write this in a classical way, we need u with two derivatives. In order to write this way, we need just one derivative and maybe one derivative in L infinity, so gradient in L infinity. Okay? So let's see, before starting, so what I will do now, I think, I want to illustrate maybe maybe you can do an exercise here in order to understand the relation between this and this. Okay? And then, so the plan is now maybe, let me see, I could do an exercise. Okay, so I will do now an exercise relating this problem with this, and then I will start to analyze a little bit this problem. And then we will go back to the relations with this one. So exercise, or maybe it could be a home exercise, I don't know, let's see. So suppose that u solves this problem, so is a minimizer. This infimum is a minimum, so suppose that u is a solution of, so let me call this problem 1, or maybe 1. So suppose that u is a solution of 1. Suppose in addition, now is a solution of 1, so it is just Lipschitz. But suppose that you know also, suppose that u, say, is C2 omega also. Okay, so I am inside this class essentially. I am in Lipschitz. So also. And now I want to show you that if I have a minimizer of this problem, so this infimum is a minimum, and is attain exactly this u, so what do I mean that this has a solution? I mean that, what do I mean? I mean that, so, I mean that 1/2 for this u here, being a solution means for me that this is equal to the infimum, the minimum integral grad v square dx such that v is in Lipschitz and v equal g on dr. So this U as a minimal energy is exactly the minimum of all possible energies of V inside the competitors Lipschitz equal to G on the boundary of omega. So suppose that U is a solution of 1. Suppose in addition that you know that this solution is smoother than Lipschitz. Suppose that you know it's even C2 inside. Then U is, so this is a, let me call this 0, maybe. Then U is a solution of 0. This is a first initial relation between solutions of the semi-classical approach and solution of the classical approach. So can you see what would you do in order to prove this remark? So this remark is morally saying that if I have a minimum point, then this minimum point must be a stationary point in some sense, as infinite dimension. When you have a function in one variable, and you know that you have a smooth function of one variable, and you know that this is a minimum point, then you know that the gradient of f here must be 0 at this point, okay? This is sort of analog, but in infinite dimension. So we are supposing that there exists a minimizer, and we want to say that this minimizer must have, in quotation, gradient equal to 0. Gradient of what? Gradient of the energy. But the energy is defined on a space of functions, so it's not clear what is the gradient. But morally, it would be, the idea is that a minimizer, even in this infinite dimensional setting, a minimizer must be sort of stationary point. And this when f is equal to 0 here, okay, so 0 is now with 0 here. So 0. So this expresses the stationarity, somehow in some sense, the stationarity of the energy functional, of the Dirichlet energy. Okay, so let us try to do this exercise. Maybe I start to do it. So let's start the proof of the exercise. Maybe you could continue by yourself, but let's see. So take phi Lipschitz in omega, and suppose that phi has compact support in omega. Okay, so what does it mean? Okay, let's draw a rough picture. This is omega, I don't know. Then f is non-zero somewhere, but is 0 out of a compact subset inside omega. So this means that I don't know where it is, but I know that phi is 0 in a neighborhood inside omega, in a neighborhood of the boundary of omega. So phi is compact support in omega. We can write this as follows: lip with a c here. by C, this means compact support. Now, why I need, this is fundamental to realize why I need the compactness of the support, because now we can consider for a real number lambda, we can consider what it is called the variation of u, simply this function here. Okay, so I take u, and I add the real number and some fixed function phi, with the attention, with the careful attention that phi must be Lipschitz. So phi must be in this class, here. And phi must be 0 on the boundary. Why we need phi to be 0 on the boundary? Well, we need phi to be 0 on the boundary for the simple reason that u here
does not affect the boundary condition.
Yes, exactly.
0, it doesn't affect to boundary.
Exactly, to match the boundary. If I have understood well your remark, is that exactly we need phi to be 0 on the boundary because we want that this variation here matches with g on the boundary of omega, because u is equal to g on the boundary of omega and phi is 0. So this u plus lambda phi is a so-called competitor, which means that, so we consider u plus lambda phi, and this u plus lambda phi satisfies the following two properties. So u plus lambda phi is Lipschitz, which is obvious because u is Lipschitz and phi is Lipschitz, lambda is a number. But also, this is fundamental, is equal to g on the boundary of omega. Why is this so? Let me repeat it. U is equal to g on the boundary and phi is 0 because there is this c here. Okay, so I can compare the energy of u with the energy of this object, right? I can compare, because this object is inside this class. Okay? Is one of these, is admissible. So what do I have? I have that the Dirichlet energy, since u is a minimizer, okay, since u is a minimizer, its energy cannot be larger than the energy of this competitor. Okay. For any real lambda. Okay. So this means that the function, this implies that now if I consider, if I consider the function of lambda, I think u as fixed, phi as fixed, and I consider this energy, the Dirichlet energy, just as a function of lambda, what it is written here is that 0 is
it's minimum, a global minimum. 0 is global minimum.
Exactly. 0 is a minimum.
So differential is equal to 0. If
yes, exactly.
If 0, 0 is equal to 0.
Exactly. Exactly. So you see, it's trivial, no? Because at lambda equal to 0, this is f of u. F of u is less than or equal than this, so it's trivial to remark that once I consider this function as a function of one real variable, thinking u fixed for the moment, u is fixed and phi is fixed for the moment, now 0 as a real number becomes a minimum point of h. Okay? And I realize also that h is differentiable, and therefore we have this stationarity condition, right? Because h is smooth enough to be differentiated with respect to lambda. And so now we want to specify what does it mean, this condition. So we have to differentiate this with respect to lambda. And let's do this computation. Let's do this computation. Maybe I start the computation. So, d over d lambda of f, so h prime of lambda, is equal, by definition, the d over d lambda of f u plus lambda phi, which is d over d lambda 1/2 integral over omega grad u plus lambda grad phi squared dx. Okay? And now we can do this, I mean, we can differentiate inside the integral. So what do we get? I think, okay, this h prime at lambda equals 0. This is at lambda equals 0. At lambda equals 0. You get grad u, grad phi dx. Do you agree with this? Do you agree with this? What do you do? I mean, this is the norm of a vector, so grad u plus lambda grad phi squared is nothing but the scalar product of this vector with itself. And then you have to differentiate this, so d over d lambda equal d over d lambda, which is equal to, then you have this, okay, simply this, divided by 2. Now, when you put lambda equal to 0 in this expression, you get this object here. Is this clear?
Yes, clear. It's clear.
No.
No. What is not clear? What is it not clear?
I don't.
Yes?
I can't say. Okay. I don't understand how it was differentiated.
This is not clear? I mean, you are saying this is not clear?
Yes.
So this is the norm square of a vector, right? The norm
Yes.
square of a vector is a vector scalar product with itself.
Yes.
Okay. So now I have 1/2 is in front. I have to differentiate this scalar product. Okay, I could write it in components if you want. It is 1/2 d over d lambda. And this is sum grad I u is the sum of all square of components plus lambda phi squared. Okay. If I write it explicitly.
Okay.
Because it is just the sum of the square of all components.
Yes.
So, sum of the square of all components. Now I differentiate with this is a finite sum. I differentiate with respect to lambda. So 2 and 2 cancel here. Then this remains. And clearly then what happens is that is equal to grad IU plus lambda grad I phi multiplied by grad I phi. Is this clear now?
Yes.
But this is exactly the scalar product written here. It's exactly this.
Yes.
Okay?
Thank you. Yes, I understand.
So perfect. Now we can go on. And so where I am here. This is at lambda equals 0. So my stationarity condition, which is written here, now let me call it stationarity condition in some sense, becomes what? That is called the Euler Lagrange equation somehow. So SC becomes what? This must be equal to 0, but for any phi.
Then this one, nabla u must be 0. Nabla u, this nabla u, gradient of u must be 0 because it's...
No, this is what we need. So this is the result of the computation. This is h prime of 0.
Yes, but...
Okay, this must be 0.
Holds for any phi, so that implies that...
For any phi, Now, let's see. So this is the somehow sort of weak formulation, of this PDE. Why? Why this is weak? Because here there is just only one derivative and not two derivatives. But now remember that we can integrate by parts. So we can integrate by parts. Sorry, I have to erase a lot of things. Poisson. Okay. So our h prime equal to 0, h prime at 0 equal to 0 is this. And now we can integrate by parts because now phi is compact support in omega. Omega is bounded, phi is compact support. We can put the derivative here and get what? So integrating by parts. And recall that by assumption now, our exercise says that suppose that U is also C2. So I can write classically, call that by assumption U is C2 in omega. Integrating by parts, what do we get? We get that this gradient here, we can put the gradient here as a divergence, okay? But the divergence of the gradient is the Laplacian, okay? So this is equal to 0 for any phi in U. Now, from this condition, since this must be true for any phi, this object here inside, since U is C2, must be equal to 0 pointwise everywhere, which means that U solves the Laplace equation. Okay, so you see, interesting remark that in some sense this PDE can often, not always, often be considered as stationarity condition of an energy functional defined on gradients. Okay, this just to tell you why these problems, this way of putting the problem are related. So one could ask for solutions of this, and one could ask separately for solution of this. Okay? Okay, now maybe I made the exercise for you, doesn't matter. I will leave you some exercise later.
Professor, I have a question.
Yes?
This 2 is equivalent or not? Namely, this infimum condition and that equation, delta U equal to 0. These two are equal or not? Namely,
sorry, can you repeat? Sorry, I didn't understand the question.
if is the solution of that infimum problem.
They are not equivalent. They are not equivalent. This is very...
Not. Okay.
They are not equivalent. Let me... Or maybe since you are asking this, I can tell you something on this. Often they are similar, often they are equivalent, but not always. Depends on G. So remember that the delicate problem is to find conditions on omega and G in order to have a solution. Conditions on the data of our problem, the domain omega and the boundary condition. And it's not clear that for any omega, for any bounded omega, say, but you can also, you see, suppose that omega is the whole space, Rn. So asking this to be finite is a sort of strong requirement on U itself. So asking U to have finite energy is a strong requirement, which is not required here at this level. At this level, when omega is the whole space, Rn, you don't ask the gradient of U squared to be integrable. So even for unbounded sets, domains, is not clear that, no? But since you asked about the, by the way, sorry, remark, maybe exercise now. Exercise, home. This is, I think, a good exercise. One advantage, they are different problems. One has advantages and disadvantages, the other has advantages and disadvantages. Concerning this, here we have fixed this integrand in this form, norm squared divided by 2. But we can ask just less than this. So suppose that now f is a smooth C2, say C2 home. Suppose f from Rn var. Suppose it is C2. And suppose that it is, well, at this level is not necessary, but I want to keep it. So suppose it is strictly convex, non-negative. Strictly convex. Suppose U is a solution of minimum problem 2, 1, 2, 0, 1, 2, solve 2. Find the stationarity equation. What kind of PDE should U solve? Solves U. Omega? Huh?
Isn't it same with Laplace equation?
Sorry?
Isn't it same with Laplace equation?
No, because phi, f is any function of the gradient, no? It's not specified. We got the Laplace equation exactly because this is exactly the norm squared divided by 2. But if you take any other convex, strictly convex C2 function, then you get another PDE, another possibly non-linear. So our PDE is linear, by the way, and linearity is exactly due to this, right? But you can imagine something else, maybe given also linear problems, but you could imagine, say, something else. So say 1 over p due to the p, dx, say for p larger or equal than 2, and less than infinity. This is one possibility. You could imagine no, 1/2. For some symmetric positive definite matrix, but any convex function which is strictly convex and C2 gives you a particular PDE. You get this PDE, this linear PDE, minus Laplace of u equals 0 only when you fix the integrand in this form. Okay?
Okay, thank you.
Okay. Okay, so this home exercise. By the way, starting from the next week, not this week, I think the next week, there will be the tutor. So exercises, all exercises here, proposed here, will be done during the tutor course. So you will find, if you are not able to do the exercise, you will find the solutions in the course, okay? Now, since you asked about the problem, the question was interesting. Suppose that omega is bounded. Can I tell that these two problems are equivalent? Namely, if I have a solution of this, then necessarily u is a minimizer of that. Conversely, if u is a minimizer of that, that is a solution of this. Okay.
I think converse is always true. Namely, u is the solution of optimization in input infimum problem. Then it always satisfies Laplace equation. I think it's true for in general.
Well, if you are not able to, yeah, but this is not enough. You should say in principle that a minimizer is C2. For the moment, you just know that a minimizer is Lipschitz. So you need this big, you need to know to prove regularity. If your minimizer is not only Lipschitz, but also C2, then you can do what we did. But in principle, you have to prove that from Lipschitz you are C2. But I want to consider the following example. So example, I think it's an old example, this. In order to answer to your interesting question, I have to say, it's an interesting question. So let me try to say a couple of words on this example here. The example says roughly, so the example will be done in 2 dimensions, and for a very smooth omega, which is the unit disk. Okay? So let me denote it simply by B1. Okay? So the open unit disk, okay, in 2 dimensions, this. So this means that omega is the smoothest omega we can imagine, bounded, and is the disk. Now there exists. The example says that there exists G on the circle. Okay, find here G. Continuous. Such that This was, I think, 0. 0 has a solution. Any solution of 0. We don't have for the moment uniqueness, so, but actually, any solution of 0 has f of u. Any solution u of 0 has f of u equal plus infinity. What does it mean? It means that the solution that we can construct in this example will never be a minimizer of that. Never. Okay, and now I want to tell you some detail. So this means that it may happen that for omega very, very smooth and bounded and very smooth, that there are continuous boundary conditions such that they are continuous but not more than continuous. No? They are not Lipschitz, of course. No? So that G there is not, I mean, just continuous, no more than that. But it exists a continuous function G such that the solution of this has always Dirichlet infinite energy, infinite Dirichlet energy. Which means that if I put that G there, I cannot solve this problem. But I can solve that. Okay? So we have to be careful about the way we decide to study this kind of problems. Okay? And now, so this is, I think, related to your question. So let me try to tell you some detail. Let me try to tell you some detail. So consider the following function in polar coordinates. Okay. We will look for, we start from this, and then we will construct G, such that okay. So consider this expression in polar coordinates. So R is in between 0 and 1, 0 and, okay. Suppose by assumption, suppose that AN and A0, suppose A0 is real, AN and BN are real for any n larger or equal than 1, and suppose, and the sum, assume this is finite. Assumptions. Assumptions. Under this assumption, it turns out that U, the series, converges. The series defining U, the series here, converges uniformly, we because you see, when r is equal to 1, when this is 1, this is finite, so it's okay. So converges absolutely and uniformly on the closure of B1. No, because we can put, okay, if r is smaller than 1, then it's easy. This is very small. But when r is equal to 1, there are problems. But if I suppose this, I get the absolute convergence. Okay, what does it mean, this? This implies that at least u, so this remark, you know, the series is uniformly converging. It means that the limit is continuous in B1 closure. Okay, and we have matched this delicate requirement. Sorry, change color. We have omega is B1, so we have at least matched this. Now to go on, I would like to have that u is solution, classical solution. Sorry, I need the definition. So classical solutions of this PD alone, so C2 solutions of this are called harmonic functions. Sorry, small space here, definition 1. If u is C2 in omega and minus Laplace of u is equal to 0 at each point of omega, then u is said to be classical harmonic, is said to be harmonic. Then we say that u is harmonic in omega. This is just a definition, just a way to put harmonic. Now, I would like to be able to say that u is harmonic in omega. Now this, it's a little bit, no. How can I say that this u is harmonic inside? I'm anticipating things that I will say in the next lecture. So, remark. So now to go on in this example, because of your question, I have to say, I need something to say in advance. So let me change blackboard, and then I will go back to the example. So in 2 dimensions, we are interested in harmonic functions. There is a very strict relation between harmonic functions and holomorphic functions. So I can so in 2 dimensions for the moment, so remarks. Suppose n equal 2, so we are working in a domain of the plane, maybe the whole plane itself. Okay. Suppose that I have this, the old f is now removed, so the old f does not exist anymore, so the symbol f is free, but the script f is not free. Script f was the integrand, but now I use symbol f, normal f, so suppose that f is holomorphic. Then, so and write it f equal, say, u plus iv, where u is the real part and v is the imaginary part.
Riemann function by Cauchy-Riemann equation.
Yes. Then it happens that then u and v are harmonic. In omega. Huh? Why is this so? Maybe this should be another home exercise. Because we have the Cauchy-Riemann equation, indeed. So, indeed, the nullity of the bar operator in omega, no? I think this is equal to df over dx minus 1 over I f over dy. So the nullity of this operator gives the Cauchy-Riemann system. Implies Cauchy-Riemann at the level of the real and the imaginary part. No, ux equal vy, uy equal minus vx. Okay, these are the Cauchy-Riemann equations. So, if f is holomorphic, then we write it in a real and plus I imaginary part. Then we know that they are related by this system of PDEs, first order PDEs. And we know also that u and v are very smooth, actually analytic, more than C1. Infinity is smooth. So we can, by smoothness, we know that u and v in particular are C2. So we can differentiate this with respect to x. Uxx must be equal to, so this is true in omega. So Uxx must be equal to Vyx. And with Vyx, now V is C2, so we can interchange derivatives by the Schwarz lemma. So we have Vxy. And now Vxy is obtained by this differentiating by y. So it must be equal to minus Uyy. Which implies that Uxx plus Uyy must be equal to 0 in omega. But this is the Laplacian of U. Okay, so you can see that the real part of an holomorphic function must be harmonic in omega. You can do at home the same computation showing that also V must be harmonic. So home, okay. So this is useful, because this allows to imagine harmonic functions, examples, no? If I have an holomorphic function, I don't know, e to the z, z to the n for n larger or equal than 1. In some cases, log of some psi, some holomorphic psi, where it is defined on its domain, the argument of psi, etc. So this, if we take the real part and the imaginary part, then we can construct explicit harmonic functions. For instance, e to the x plus iy, so this is e to the x cos y plus I sin y. So this means that e to the x cos y is harmonic, e to the x sin y is harmonic in R2. Or also z to the n, for instance, z squared equal to, so x, I mean, you can write exercise home, write this, the real part and the imaginary part are polynomials of degree, real polynomials, homogeneous real degree polynomials of 2 degree, second degree. Write these polynomials, the imaginary part, and check that they are harmonic, and also for z cubed. Check they are harmonic. Harmonic in R2, for instance. So this is a remark that it is useful here, because you see, now, okay, R to the n this means that each addendum here, no, separately, this object here is harmonic. So if I multiply by a constant, it remains harmonic. And the same for this. So at the level of a finite sum, so and the sum of harmonic function is harmonic. Why? Because the Laplacian is a linear differential, is linear. So if I take the Laplacian of the sum of two functions, is the sum of the Laplacians. Okay, we have linear PDE. So this means that a finite sum of these, this is a constant, so trivially harmonic. But this means that if I fix n, then say n larger or equal than 1, then the sum from 1 to n of what? Of this is harmonic. Is harmonic in our disk B1. Actually, is harmonic in the whole plane. Is harmonic everywhere, but in particular here in B1. The problem is that here we have a sum. Now, there is a result that says that the class of harmonic functions somehow is closed under uniform convergence. This we will see later. I cannot prove it now today because we need some results. But just to motivate this, that is the limit as a capital N goes to plus infinity of these objects. Each of these is harmonic and the convergence is uniform. Under these assumptions, it is possible to show that also U, the limit, the uniform limit, is harmonic in B1. So this I don't prove it. We will prove it later. So, but now, so it is later. We will prove that in one of the next lecture of the next lectures, we will show that the uniform limit of harmonic function is still harmonic, and therefore that U is also harmonic. Harmonic in B1. Okay. Now, harmonic in B1 means, in particular, also C2, actually even more. So this is, so at the end, what do we get? We get that U is C0 and harmonic. Inside Okay. So we have found a solution of this, and who is G? Well, G is, you put R equal 1 here. When you put R equal 1, you get G. Okay, because you are on the boundary of the disk. When R is equal to 1, you are exactly here. Okay. So we have found a solution, and now we want to choose the coefficients an and bn in order to make the Dirichlet energy plus infinity. So now the next step is to choose, cleverly choose, an and bn, because this is what I have said is independent of the choice of an and bn. For any an and bn satisfying this condition, essentially what I've said is correct, I hope. So now the point is to choose an and bn, no? So next point. Next point, now we want to choose an and bn satisfying this, no? In such a way that f of u is plus infinity. Well, first of all, let me recall you the expression of, so the f of u, remember that f of v, say, is equal to and we have that, let me recall you that in polar coordinates, this is equal to dr v squared plus 1 over r squared d. Okay, so when we want to write our energy in polar coordinates, we have, of course, to put here a Jacobian determinant, which is r. Okay, and then so we will have to work with this object here. But before doing that, so we have to learn how to make the derivatives of this object, this series here. Now, you can see that if we do the derivative, here, I mean, we can show that X may be home for any r now less than 1. So if I stay inside, so if I don't go too close to the boundary, so if I work here, then here, because when I differentiate with respect to r, what I get here, there is an n in front, n r to the n minus 1. And this n could destroy this convergence, but when r is equal to 1. When r is smaller than 1, we have this power here, r to the n minus 1, which makes the series convergent. So, for any r less than 1, we can differentiate the series term by term as soon as we are far from the boundary, from r equal 1. So, for any r less than 1, say in 0, 1, then dr u is actually the sum n r to the n sinus theta. Stop me if I'm making some mistake. So this is okay for any r as soon as we are not on the boundary, because the series, this series is uniformly converging on compact subset of B1, and also this, okay? So we can differentiate the series term by term. Now, I have to compute this and this, because this is my integrand, okay? So, what do I do? Can you help me to do this? What should I do? I have to take the square of this series, right? How can I compute the square of this series? It's difficult.
Minus terms cancel.
Yes, you're right. It's Parseval Identity. It's the Pythagorean theorem in infinite dimensions. It's the Pythagorean theorem in Hilbert spaces. Why? Let me explain this. Thank you for the remark. So this I keep. Now I need another. No, I have that. So remember that in L2 of 0 to pi, the system, there is a constant here, maybe. Okay.
Orthonormal basis.
This is a complete orthonormal system. So we have the Parseval identity, which says that to compute the square of this object, we just need to compute the sum of the squares. So Parseval So what do we get? We get that this, as soon as r is less than 1, this is equal to, of course, n equals from 1 to plus infinity. Then what do we have? We have, maybe there is, because this is not divided by square root of pi, so I think there should be, please check, there should be a pi here. So let me see. 2n minus 2. And the derivative with respect to u square, for the same reason, is the sum from 1 to plus infinity n squared. Now there is 2n here, but we have essentially the same quantity. No? Now the interesting remark is that you see, here we have here we have r to the 2n minus 2. Here,
I think we have integral in front of this.
Pi, sorry, you're right, there is pi.
This side. Integral, because integral of this square.
Yeah, but now you see, now what the comment is that if I look at the gradient in polar coordinates, I have an r squared on the denominator, no? So if I have, if I divide this by r squared, this is exactly the same as this. Okay? They are equal. So now, to be even more rigorous, one should do what? To show that this will be infinity, one should integrate between 0 and r, and then in the end let r to 1, to be very precise, because all these computations are valid from 0 to r. But let me skip, this is just a small, okay. In any case, this is equal to 0 to pi, the integral from 0 to 1, and then one of the two, because I have removed the 1/2, these are equal. So I remove the 1/2, I just keep one of them. So I have pi here, sum
I think we can cancel the first integral, because in our previous integrals we take into account this integral from 0 to 2 pi.
Yes.
In our previous formula, so we have to put integral in front of this square
this pi
derivative.
Let me just check the constants. So 1/2 disappeared. The pi should be in front there. This is independent of theta. But there are too many pi's here.
That is in Parseval equality.
There is also the r. So we have 2n minus 1 now. And then I have dr d theta. But you are saying that I made a mistake in the constants here?
No, Professor, in Parseval equality.
Parseval identity?
Yes, in identity, in the left-hand side.
Left-hand side?
We have to put integral in front of that square, in the left-hand side, because integral from 0 to 2 pi.
Yes.
Yes.
There is you're right, there is a missing integral here, and there is a
second one also.
Yes, of course. Parseval. Thanks. This is Parseval. Okay. Okay, you are right. I made a mistake here. So Parseval is in L2. L2, 0 to pi, with respect to theta. Thanks. So we are here now. And now we choose the coefficients. We choose now n equals 0 for any n, and bk equals 0 for any k different from n factorial, and bn factorial equal 1 over n squared. I think this should be so let us compute this quantity. So this is what I have. So n square is outside, the series is outside, everything is outside. Pi is there, so this is equal to what? It is pi, the sum, n square. Now you have to integrate this, so there is 1 over 2n. And then I have an squared plus bn squared. Right?
Yes, it's right.
Because I have integrated this power here from 0 to 1, 1 over 2n. So pi sum pi over 2 now if I choose, so this is the Dirichlet energy now, okay, this is the Dirichlet energy. Now let's choose an equals 0 identically, so take some square. And now I choose, as I said, this. So it is 1 over n square. En is 1, so it is n over n to the 4. And the radius, there is, okay. N. There is something wrong, probably. Integral from 0 to 1. N bn square. Yes. There is something wrong. Pi square. When, let me see what's happening here. Because maybe I forgot this. So you with that choice you becomes sum 1 plus infinity r to the n factorial. In is 0, bn is 1 over n squared, right? Sinus n factorial theta. This is you with that choice of an and bn. Okay. Okay. Now my Dirichlet energy is what? My Dirichlet energy is of you. I have an n factorial which is missing somewhere. Factorial. There is something I am missing here. Rn. Because of course this is converging, but there should be some n factorial here in front, which at this moment I have missed. Can you see where I have missed this n factorial? Ah! Because, no, sorry. This n here is not n, but I sum only on the factorials. So this is n factorial, by choice, no? Bn is always 0 when bk is 0, unless k is equal to n factorial. And therefore here, when k is equal to n factorial, when n is equal to n factorial, this is n factorial, then Bn, which is 1 over n squared. So n factorial divided by n over 4. Which is plus infinity. So if this is not wrong, check at home. Who is G? Finally, G is equal to this when R is equal to 1. So G of theta, at the end, the claim was that there exists G continuous. So G of theta should be exactly this. When R is equal to 1. So G is simply, it's not simple at all, but it is this. This is G. This is continuous. And this U is an harmonic, and this U here is an harmonic extension of this, so it's harmonic inside, and its Dirichlet energy is plus infinity. If the computations are not wrong, it seems to me that this is more or less answer to your question. Okay, sorry, I am late.
Thank you.
Thank you.